3, and that is my 5. Force diagram, come on.
Force of tension.
Going which way on what?
Up on 5 kilogram mass. Down on the 3 kilogram mass. Or down.
Not down.
No, to the left.
Okay, where it is in that drawing to the left, towards the center, but we'll just take a sort of a snapshot when it is on the, from our point of view, on the right side. So I got tension acting that way, okay? Table's frictionless, by the way.
Gravity and down on the 3 kilogram mass, the weight.
Okay, so I have weight acting on the 3 kilogram mass, so W sub 3.
And down on the 5 kilogram mass.
All right, W sub 5.
No more force pushing up on the 3 kilogram mass.
All right. I didn't include the string, so I'm not worried about that, or the table, but these are the two I care about. All right, so that is force diagram. The direction of acceleration. In which direction will 5 accelerate?
Hit 1. You said it's at equilibrium.
Yep, therefore,
It won't.
okay.
No acceleration.
So there's no acceleration. It really, so it makes incredibly little difference whether you want up to be positive or down to be positive. All right. We'll make up positive. All right, which direction will the 3 kilogram mass accelerate?
Towards the center.
Yeah. It's traveling in a circle, the acceleration would be towards the center. It's centripetal acceleration. So I have acceleration going in this direction. And so I'm going to set up my coordinate system, which is the next, so force diagram, acceleration, coordinate axes. I've already established that one. But I'm going to make to the left positive, so I'll make that sort of an I hat, and I'll make up positive J hat. Decomposition, what vectors do I break up?
No.
Okay. Equations of motion, how many equations of motion will there be?
2.
Which do?
Weight and force.
Or, no, weight and tension.
The weight of what?
Weight of the mass.
The weight of the masses, so if that, is that one equation or 2? All right, the question was, for those who missed it, how many equations of motion will there be? So you just count up the axes that were required for each one. I got 2 there and 1 here. There will be 3 equations of motion. So I'll have the I hat for the 3 kilogram mass. I'll have the J hat for the 3 kilogram mass. And then I'll have my vertical for the 5 kilogram mass. However you want to notate it. All right, somebody give me an equation.
For I had 3 kilogram mass would be Y minus.
Oh, it's J hat.
Oh, sorry.
Y minus.
Weight sub 3 is equal to 0.
All right. 1 down, 2 to go. Again, our template, Newton's second law, F equals mx. Let's go ahead and get rid of those.
acceleration minus the weight, 5 kilogram equals 0.
Okay, one to go.
Maybe force of tension. Maybe plus acceleration or minus acceleration? Minus acceleration.
Oh, on,
Yeah.
you want minus, it's not, on the left-hand side are the forces, acceleration is not a force. Equals.
Equals 0?
No, not 0.
That's what acceleration.
Because this is traveling in a circle, that acceleration is centripetal, so I can put a little c there just to remind us. So yeah, it's a very simple equation, it's just I have one force acting in that direction. This is my centripetal force, because that is the force pointing towards the center. So now, substitution. For what do we have an independent formula? Yep, and the acceleration. All right, so for weight, I know that's mg, so my equations become an A, we just figured that out, that's v squared over r. So my tension is equal to mv squared over r. My normal force is equal to m3g. And down from here, my tension is equal to m5g. There's no friction, so my normal force equation is not going to do anything in this case. But I have two equations here set equal to tension. We can just set them equal to each other. Ultimately, we're solving for v. So mv squared over r, that's m3, is equal to m5g. So v squared is equal to m5gr over m3. And therefore v equals the square root of 5 kilogram mass times acceleration due to gravity times the radius over m. That's supposed to be a 3, it's not a 5 there for m3. And now we plug and chug. Square root of 5 times, let's put it on Earth 1, 9.8 times the radius of 0.1 divided by 3. And we end up with
1.29
units.
meter to second squared.
Too far.
Meters per second.
Oh, yeah.
Just speed. So if that 3 kilogram mass is cruising around at 1.29 meters per second, that 5 kilogram mass will stay in equilibrium. If it travels faster than that, it's going to move a little bit further from the table, or from the center, and this mass is going to rise. And if it's slower than that, then the 5 kilogram mass will fall, 3 kilogram mass will get sucked in towards the center. Questions here before I make it a little more difficult.
So you had a normal force upon the 3 kilogram block,
Right,
and I know that the other one's going back on the table.
correct.
Do we not work with that at all?
No, if we were doing the full force diagram, yes, we would have drawn that, but all I cared about were the two masses, so I didn't really care about the table for this problem.
But it's just assumed that there's a pair with it.
Oh, yes, absolutely. It's part of the art of this is knowing when you can ignore certain things. Since the question was about the 3 kilogram mass, how fast is the 3 kilogram mass? So I knew I definitely needed the forces on that. I mentioned the 5 kilogram was in equilibrium. We definitely needed forces on that. The string is ideal, so there's going to be the tensions on the string and a normal force, but ultimately with the string having no mass, this equation right here doesn't help us at all for massless objects. And the table is just sitting there. I'm assuming the table is not accelerating. So that's my justification for leaving those out of my force diagram. I could have included it, and then ignored it later.
Would it have changed the equations?
Depends. What's the friction situation between the table and the ground? That becomes key. If it's frictionless between the table and the ground, then we've got this, so let's throw that into it. So I had, if I threw the string in and the table, I would have tension on this end of this string and tension on going in that direction on that end of the string, and that's supposed to be a T. I'd have a normal force here, just Y sub R for rope, and then there'd be a normal force acting on the table there. That normal force, though, is at an angle, which means there's some horizontal component. So if there's no friction between the table and the ground, so the table's free to move, what's going to happen is the rope is going to push on the table and the table's going to move this way. As the rope swings around, the table's then going to move. And so basically, it's the string is zipping around the hole there, the table is ultimately moving in sort of the opposite direction. See, if it's moving this way, the table is being pushed that way. No, it's moving from there, it's going to be pushed. So no, they're going to sort of rotate together. Anyway, the table would start moving around. My intent was the table does not move. So therefore, its acceleration is 0. And we could have analyzed the forces acting on it, but if the table's not moving, it's the only thing that it's doing to the problem is changing the direction of the rope from vertical to horizontal, or vice versa. I feel like it's not a satisfactory explanation.
Could
But-
you tell us, ignore the table in this problem, or should we just know to want to ignore things?
If I want you to include the table, if I said, on a problem like this, I'd be more apt on a quiz or test to say, what are the forces acting on the two masses? Granted, the table is a mass also, but I would have referred to the 3 kilogram mass and the 5 kilogram mass. If I wanted the full force diagram, I said, what's the full force diagram of the masses on the table and the ground? So I should be giving you that, and if in doubt, then ask.
Okay.
Other questions? Let's make it more difficult. Because that's what you really want, for sure. This time, we won't have the table. I'm just gonna have a tube here. I got a mass hanging down below it, and then I got my string. So I'm gonna call this A and B. So basically, it's the same type of situation in the fact that this is going to be in equilibrium. And I'm trying to figure out Well, what do I wanna figure out? I wanna figure out, we'll just say V for right now. Let's do it. Let's just do the whole thing. So I got A here, I got V, I have the tube, and I've got my string. What are the forces acting on what?
The way acting down on A.
All right? So I got W sub A. Oh, let's throw the ground in there also. So W sub A. All right?
The way acting down on
W sub B. W sub B.
Tension on A towards the string.
Towards what?
Towards the string. Or towards
Okay.
the string.
So I have this tension on A.
And then the opposite on that, the string.
B. Tension acting up on B.
If something's holding it up, all right?
And down on the string.
I am assuming that there's no friction between the tube and the string, and the string's massless, you know, and stretchless. It's an ideal string. Or as Miss Sasso would call it, I believe she calls it a matching string.
The normal force on the string
From,
from the tube.
yeah. So it's flowing in that direction somewhere, so call this Y sub S for string. And where's the other part of that pair?
B down, the opposite angle on the tube.
How's the tube staying up?
Normal force on two.
Say it again?
And normal force up on two. Does the tube have
Oh,
weight?
from what?
Does the tube have weight?
Yeah, so let's put a weight of the tube here, so W sub T, W sub T.
Isn't that what normal force is? The force that holds it up?
Is,
And up?
If there's a normal force up on it, that means that it's sitting on something.
Oh,
is B on the ground?
No, B is not on the ground. The ground is down there. All right, I didn't actually state it in the problem. Somebody's holding the tube in the hand as it's swinging. So it would not actually be a normal, well, there is a normal force between the hand and the tube, but that's horizontal. It's actually friction holding it up. But there's some mystical force acting upwards, and so this would be an example of other. So I've got some force acting upward that's holding it up. I'll just label this friction, but it doesn't really matter what it is. Now, I could have included the person into this problem and have his hand on the tube, in which case then suddenly we're bringing the person into it, and he has its weight, and there's friction with the person, and the person's gotta be standing on something, so that's the ground or floor. I mean, at some point, we need to stop, because if I'm doing this in the building, the floor is attached to the walls, and the walls are attached to the ground, and, you know, you could keep going on and on and on, so at some point, we stop. And I'm just gonna stop it there. Someone's holding the tube, swinging it around. So, but what I really care about is the two masses. So let's do the analysis, just those two masses. in what direction is mass B accelerating?
It isn't. It isn't,
Correct? Why?
because it's in equilibrium.
In which direction is A accelerating?
Towards the center.
In which direction is that? Point with your finger. So, the circle it's traveling in, for those who didn't look, they were pointing that way. So the circle is traveling in a circle like this.
Towards the string?
Towards the string. Isn't that the same direction you just pointed in?
Yeah.
What is the circle that it's traveling in? Yeah, where's the center of that circle?
At the two.
But in terms of finger direction, that way. Two's long, we have to be more specific. The acceleration of mass A is that way. It is not that way. That's probably the biggest mistake. You have to think about what is the circle. I didn't state it, so for those who read my mind, thank you. It's traveling in a horizontal circle, so acceleration is to the right for mass A, and there's no acceleration here. So our coordinate axes here, up or down positive. I'll call this J sub D. And over here, my acceleration is towards the center, so I'm gonna have one of my axes that way, and because I've been brainwashed, I hat, A. And then J hat, it's perpendicular to that, up or down, it doesn't matter. Luis, you seem to have to pin down, okay. So we'll make J hat down, J sub A. So we've done the forces, we did a direction of acceleration, we did our coordinate axes, and now decomposition.